Tsai from UBC. And today he's going to talk about the Green's function for non-stationary Stokes systems in the half space.
Okay, so it's my turn. I'm very happy to be able to speak here. I thank Hongji for the invitation. So, so this talk is about the green tensor of the non-stationary Stokes system in half space. So here are my collaborators.
So Tai-Peng, actually, I cannot see your slides.
You cannot see my slide?
No.
Yeah, same here.
Just make it to full screen and then it disappear. Okay, so maybe I don't make it full screen.
Okay.
I think you can do it, but maybe you should first make it full screen and then share that screen.
Oh, okay. Okay,
so
that's
if
a good
you prefer
idea.
that, try it.
Next page. So here are my collaborators. Kyungkeun Kang, he was also from Minnesota. He's now in Yonsei of Korea. And Baishun Lai was a visitor. He's in Hunan Normal University. And Chen-Chih, he is my current PhD student. He will go to Columbia University in August. So the outline of my talk, there are 3 parts. The first one, I give an introduction. The second part, I will describe our main result. And the third part, I will sketch the main estimate. Part 1, introduction. So here, the Stokes system in the half space. So dimension n is 2 or higher. And my notation here is that x has the first n-1 component, we denote that as x prime. X prime is the tangential variable. And then the reflection is denoted as x star. X star has an opposite sign for xn. And then our upper half space, Rn plus, is where xn is positive. And its boundary is denoted as sigma. So it's where xn equals 0. We consider the non-stationary Stokes system. So this is ut minus Laplace u plus gradient pi equal to f. Divergence is 0 in Rn plus times 0 to infinity. And we have initial and boundary conditions. Initial condition is u0. Boundary condition is usually 0. And so here, u is the velocity. And then pi is the pressure. And this is the force. So that's the Stokes system. And there are, I give 2 solution formulas here. The first formula here is given in terms of green tensor. So it's a Gij. We have a system, so we need a tensor. Gij syt. And then a solution of the Stokes system is given by this formula. The first part corresponds to the initial data u0. So Gij times the jth component of u0, and then integrate in y. And then the second part is for the fourth term, Gij times fj, and then integrate over space and time. And then a more common formula is this form. So this is a Duhamel's formula form. And then, so here e to minus ta is the semi-group. So A is the Stokes operator, is the minus projection times Laplace operator, and P is the Helmholtz projection. It maps a vector field to a vector field which is solenoidal. And I will describe that in a moment. So this is the Stokes operator. And then this is Duhamel's formula. So we also take projection over force and then apply this semi-group. So our green tensor can be considered to be the kernel of this. It's important to keep in mind that I need to keep this P here. P is important. So here I describe what is solenoidal vector field. It's because that the Stokes semi-group and the Helmholtz projection, they cannot be defined in any space. And so when they are defined, the image should be solenoidal. A vector field is solenoidal if it is divergence free. And moreover, its normal component should finish on the boundary. So an equivalent definition when U is L1 local up to boundary is that it is orthogonal to any gradient field. If phi is smooth with compact support, but in this notation, my phi could be non-zero on boundary. And then the initial condition is understood in the weak sense. So we multiply ut by any smooth test function. And then the limit should converge to u0 dot product with w. And this w here is so relation here, C is compact support. Sigma means solenoidal, it's divergence free. So my compact support, W is not zero. I'm sorry, W is zero on boundary. So I don't need this condition here, just divergence free. And then this is a weak limit. And a strong limit is usually wrong because we expect this limit to equal to the projection of U0. So this is about solenoidal vector fields. And now, for my purpose, I want to consider its applications to Navier-Stokes equations. So usually we write our Navier-Stokes in this form. We move linearity U dot gradient U to the right-hand side. And a solution is called a mild solution if satisfies 3 or 4 with this thing as the source term F. So 3 and 4, let me recall, 3 is this source formula here, and 4 is this integral formula, integral equation. And so such solution is called a mild solution. So this does not include those weird solutions that there are some weird solutions, but they don't satisfy the integral equations. So this guy kills them. So when we look at the formulas here, we can assume our initial data is solenoidal, but we cannot assume F is divergence free because our F for application is this guy here, U dot gradient U, it is never divergence free. And so it's important that we cannot remove P in the formula here. This P has to be kept here. And that's usually the difficulty. And then, okay, but now 3 does not contain P. There's no P here. And the reason is that P is already part of the green tensor. So here I talk about norm estimate for the Stokes equation. So the first part is the Beck and the Sobel spaces. So for estimate in this spaces, it's similar to the Rn case because the Stokes semi-group and the Helmholtz projection, they are bounded in LQ, if Q between 1 and infinity. And so there are many previous results. And then the second group of spaces is using weighted pointwise bound. So I want the solution to be bounded by, okay, my initial data is bounded by C over 1 plus X to some power A. And then I want the same property to hold for solution at time T. And is it true? It's actually, it is known if U0 is solenoidal, and it was unknown if U0 is not solenoidal. And this is important because our F is not solenoidal. And how about this space? Here the decay is only in Xn. We don't include the tangential decay here. So if U0 is bounded by this, is this preserved by time evolution? And this was unknown, even if U0 was solenoidal. And then the third group of space is uniform local LQ spaces. It's LQ uniform local is defined to be, you take LQ norm in a unit ball, an intersection upper space, and then we take soup over the center of the ball. And the estimate in these spaces was recently done by Maekawa, Yura, and Planche. And now I want to talk about special cases of the green tensor. The first special case is the restricted green tensor G brave IJ of Solenoid. So for the special case when both U0 and F are solenoidal, Solenoid have found this formula. So this formula is in terms of G brave. So this works here. And there are explicit formulas for G brave. Let's look at this. So the main part is the gamma, which is the heat kernel. And this correction part, Gij star. And Gij star has two parts. This part is also heat kernel, but with centered at the reflection of Y. And then this part here is a space-time integral. I'm sorry, integral over space. And this is over tangential component. And in normal direction, it's only over interval from 0 to xn. So this is quite special here, from 0 to xn. And then it's also important to learn that we have 1 minus delta Jn here. So this term is 0 if J equal to n. And here, my formula here, E is the fundamental solution of Laplace operator. So this is the restricted green tensor of Solenoid. And here is estimate for the correction term. And let's look at the estimate here because we're going to see them later. So first, normal derivative partial in Xn is exponent k here. It only gives us a normal decay. So this is only Xn, it's decaying Xn. And however, for tangential derivatives, we have arrow shows up here. We have a decay in tangential and normal directions. And then if we differentiate in Yn, we don't see it. Yn is Q, we don't see it because we have exponential decay in Yn here. And finally, time derivative does not give us any decay. So time derivative gives us this singularity here. And then this is for the correction term. And now let's compare the ocean tensor, which is the fundamental solution for a Stokes system in the whole space. So it has a explicit formula, delta ij gamma plus gamma ij, and gamma ij is given by this formula. This is basically the Lewis potential of the heat kernel. So di dj heating on E will give us the singular integral corresponding to Lewis potential. Lewis transform Ri Rj. And then so they have this estimate. So x squared plus t and to the correct power. So you can see the direction. There's no distinction between direction. It's always all derivatives give us one extra decay in space. So this is estimate of Solenoid. Another special case is due to my collaborator Kang, but he's only in this case that Ya is equal to 0. And so when Y is equal to 0 here, this estimate, and then and alpha here is any number between 0 and 1. So there's a singularity near the boundary, but it's integrable. And the question, the starting point of our project is that the anyone study the full unrestricted green tensor and its pointwise estimate. And so far, I think nobody really studied this guy. So now I explain our motivation. Motivation for unrestricted green tensor. So first, to construct solutions satisfying this pointwise the weighted pointwise bound. And then we cannot use the Solonikov's tensor because this F is not divergent free. So what people did was that you look at the linearity, which is P partial K U K U. What they did is that they use the explicit formula of the Helmholtz projection and expand this guy to many terms, and then they estimate each term. So this can be considered to be a bilinear estimate. But I think it's maybe more complicated than bilinear estimate because each term may have different estimates. So you can see a few partial results. Crispo, Mario-Monti, they consider case for dimension 3 and higher, A between 1/2 and n. And Chang and Jin, they improved. A is anything between 0 and n, including n, and n can be 2. And then when there's no decay, A equal to 0, Solonikov and Mario-Monti, they did this for data which is continuous and solution is continuous in time. And then Bay and Jin, they did a case in L infinity. So one drawback of this approach is that it does not apply to general linearities. So for example, you can look at F equal to this form, and they just give some structural bound. And then there are also some natural linearities coming from coupling. So for example, in a metric D, there's one source term Fj, which comes from, is of this form, where BKBJ is the magnetic field. And then in the lemmatic liquid crystal flows, there's a source term of this form. And then here D is a orientation field. It's the target of D is a unit sphere. And the boundary condition of D is it's a normal derivative is 0. So these guys, they have different boundary conditions. So the previous thing you have to does not work. And also, if we change the weight, for example, we change the weight to be this thing here, but xn here, then had to do everything from the beginning. And second motivation was the mild solution in LQ uniform local by Maekawa, Mura, and Planch. So the approach is based on resolve and estimate. And they also need to prove bilinear estimate. So we want to give a second proof. And third motivation is that pointwise estimates are useful for local and asymptotic study. And so Kang has an example in 2005 for Stokes flow. This flow is a Herder continuous up to boundary. And it has unbounded normal derivative in a region near boundary. And then this is caused by a non-zero flux on boundary away from the singularity. So this is a very significant example because this is different from the interior case. So even for Hertz continuous solutions, the derivative will not be bounded. And then his example only for Stokes. Can we use that to contrast solutions for Navier-Stokes? The essay is that we cannot if we don't have pointwise bound for green tensor. So this was a major motivation for this project. And then Serakin and Spheric, they have a shear flow example, which is after this paper. This shear flow example is very nice because it solves both Stokes and Navier-Stokes and has zero boundary value. But then the problem is that this is a shear flow, so this shear flow has no decay, so it does not have finite energy. So these are our motivations. Okay, I need to keep track of the time. Okay. So here I want to compare what we know for stationary case. So I put upper zero here to mean stationary case. So for green tensor, it is well known that it's bounded by this. If y is of order 1, so that corresponds to force with compact support. And then in a previous work with Kang and Mura, we show that we will show this estimate here. So this thing, this xn, yn on top, x minus y star here. So this thing here is basically an additional factor. And moreover, when we have no normal derivatives, we just take tangential derivatives in x prime, y prime, this kind of estimate. So we compare this with this. The tangential decay is better. This is better than this. So if we fix Sn, Yn, and then this will still have power n here in the decay. And here is only power n minus 1. And our intuition is that the better tangential decay is due to the zero boundary condition. Okay, so that was the introduction. Do you have any questions so far? Okay, now I describe our main result. The first result is the symmetry. So for nxy in upper space and non-zero time, gij xyt equals gji yxt. So we switch x and y, we also switch I and j. So this was known for the stationary case. And it was unknown for non-stationary case. And it is false for the tensor of solenoid. This is the first theorem. The second theory is about the restricted green tensors. So this is solution formula for initial data U0. And we can use 3 different tensors here: Gij, Gij brave, and Gij height. And the Gij brave is the tensor of solenoid. And Gij height is defined by this formula here. So here's heat kernel at the reflection point. And then there's a new term, Ci. And Ci is an integral. Also over this space region, it's a sigma, the boundary times 0 to xn interval of something here, heat kernel and the polynomial solution. And so there are some 3 things to observe here. The last term of G brave, this guy, only acts on the tangential component. We mentioned that earlier. And then the last term of G hat, this term here, only acts on the normal component because this is 0 if J is less than n. So this makes this tool special. And the second comment is that any Gij bar given of this form, so it's a Yj derivative of some vector Ti. Any tensor of this form with a good regularity and decay will fit into this formula here. It is also a restricted green tensor. So there are infinitely many restricted green tensors. And in contrast, the unrestricted one is unique. So these two are very good because this guy basically has the best estimate. This guy, the estimate is not as good. However, it only acts on normal component, and if U0J is solenoidal, then this guy finishes at the boundary. So we have better regularity near boundary.
I have a question.
Yes.
What is T here?
T is any tensor.
Any tensor.
Any tensor.
I see. And also, is this G hat used by Ukai in the paper?
No, no. I think G hat was I think it's found by us. I didn't know this guy before we do this project.
I see. Okay. Thanks.
Ukai's formula is in terms of Lewis transforms, and it's good for LP estimate, but it does not. It's not good for pointwise estimate.
I see.
Yeah, it's good for LP estimate, not for pointwise estimate.
Thank you.
Any other question? Okay, the third theory is about convergence to initial value. So we look at this solution here, this formula here for initial value U0. There are three cases. The first one is the easiest. U0 is C1 with compact support. And then we don't assume divergence free. Then the solution converges to PU0 for all x. And then it's uniformly if xn is away from the 0. So it's uniformly for xn greater than delta, for any delta. That's the first case. But the second case is for LQ. Q is between 1 and infinity. In this case, you convert to PU0 in LQ. The last case, U0 is a C1C and divergence free. And we put sigma here is solenoid, but we also put a bar here. So it does not need to be 0 on the boundary. So because it's not 0 on boundary, so its divergence should be 0. And also the normal component should be also 0. So that's what we mean by solenoidal. So U0 is solenoidal and C1. Then you convert to U0 because U0 is equal to its own projection. And this is true in LQ. The important thing is that here my Q can be equal to infinity. So I just want to mention that to prove this C, we have to use both G breadth and G height for different Q. So I think for big Q, we use G breadth. For small Q, we use G height. And that's because we have boundary singularity. We need this guy to take care of boundary singularity. And then steering 4 is our main estimate. So Gij is our unrestricted green tensor. We have tangential derivative, normal derivative, and time derivative. And this part here comes from the He kernel, or it's the same as the Ocean tensor. And this part is the main thing. And so here, Ln here is some little correction for dimension 2. So you can forget them. For dimension n is 3 or higher. You can think of it just 1 here. And then this part is decay in all direction. This part is a normal decay. So normal derivative only give us normal decay. And moreover, we may lose a number sigma. IJKQ defined here, and it's up to 2. But okay, it's not lose, we can improve decay. So we can move up to 2 decay, normal decay to tangential decay. This is very useful in some cases. And then time derivative only give us this singularity here. And theorem 5 is on boundary finishing. So we take any alpha between 0 and 1. If we don't have normal derivative in xn, then we have this power here, xn here. And so this shows that this guy should be 0 as Sn go to 0. And that's reasonable because our Gij has 0 boundary condition. And we also have similar estimate if Q is 0 and K is positive. And so this is similar to our estimate for a stationary case. So here's an example in R3 case. In R3 case, the stationary green tensor has this estimate. And the non-stationary green tensor has this estimate. In contrast, in the whole space, this is a fundamental solution, has this decay. And this ocean tensor, this is time-dependent case, has this decay. So this guy, compare these two guys who have this extra factor, it gives us an extra tangential decay. And compare this guy with this guy. So this is extra factor. So this is only X3. So it does not give us tangential decay. What it shows is boundary vanishing. And that this thing is actually integrable in Y for fixed X, but it's not uniform in X. So, but it's still integrable. And now we talk about applications. So first, we'll give new proofs of the existence of Miles solutions, local in time Miles solutions in these three classes. The first one is the classical LQ, for Q from n to infinity, up to infinity. The second one is in this pointwise weighted bound. The third one is in LQ uniform local for Q greater than n up to infinity. And the second thing is we recover this estimate for gradient U. This was done by Giga, Matsui, and Shimizu. And the initial data does not need to be solenoidal. This is tricky because I think resolvent estimate does not work in L1. So resolvent estimate does not work in L1, so one need to be careful. And then, but this is true for gradient estimate. And the third application is on this singular boundary singularity. So Kang has a solution for Stokes system. We use that as the profile to contrast solutions of Navier-Stokes, and it satisfies the following. So first, it has 0 initial data and 0 force. And it has a Herder continuous boundary data with compact support. And second, this solution has pointwise bound. So the velocity is bounded everywhere. And it also has finite global energy. So L2 known here, this is whole space. This is uniformly bounded in time. And then the gradient U squared space-time integral is also finite. And third, it has an unbounded normal derivative for tangential component. So dn is a normal derivative. U prime means U1 up to UN minus 1. This is a tangential component. So the tangential component of the derivative of the velocity normal derivative, you fix x prime and take xn to 0 is equal to infinity. And this is true for n x prime bigger than a constant. We basically want this s prime to be away from the support of the boundary data. And so this is, I think this example is interesting because this guy has finite global energy. So the example of silicon spheric is very, very simple, but the energy is infinite. So for our study of the regularity problem and the existence and the uniqueness, I think finite global energy is very important.
Is there a, usually you expect the energy dissipation, right? Do you?
Yes.
So is this example, like, does the energy dissipate or it just stays bound?
So I guess not, because we have input here. We have a boundary data.
Ah, okay.
Yeah, so the singularity is all due to this boundary data. Of course, if we don't have input, we don't know anything which we grows up.
Right. Thank you.
Yeah. So the example of circuit spheric, they don't have boundary data. But the only thing is that the energy is infinite. So now I want to sketch the main estimate. So here I describe what we want. So this part is the Gaussian tensor. So the phenomenon solution in whole space. Its estimate is very simple. So I don't put the time derivative here. Just look at the space derivative arrow here. So every derivative give us one actual exponent here. So if arrow is equal to 0, this is just n. So it's not integrable, but it's weak L1. So this is our wish list. We want our Gij to be in weak L1 in Y. So at least like this. Maybe not as good, but the weak L1. And the second thing is that we want the derivative of our gradient over our tensor to be L1 in Y. So if we have L equal to 1 here, this n plus 1. N plus 1 is integrable. So we want this guy to be integrable. And this is very important because for our solution, for our application to Navier-Stokes, we have U dot gradient U. So we can move the gradient to the green tensor. So we have one derivative in Y. And so if that guy is integrable, then our integral formula will make sense. So this is important. And then what we learned is that normal derivative only give us normal decay. It does not improve tangential decay. And this part here includes normal derivative. So to be in L1 in Y, this guy is not L1 in Y. So to be L1 in Y, we want this thing here, number 3 here. We want the integral offers tangential variables to be finite. And for any yn greater than 0. And then this normal derivative will improve normal decay. And this normal decay will help us to integrate this further in Yn. So we need these 3 things. And then the most difficult thing is to find a good formula. So here is our first formula. So our first formula, we have a Gij tilde plus Wij. Wij is a correction term. And Gij tilde is given by Gaussian tensor minus Gaussian tensor at the reflection point. And epsilon j is equal to 1 for j less than n, and epsilon n equal to minus 1. And then, so this Gij tilde corresponds to solving Stokes system in the whole space for arc extension of the initial data. So arc extension of data means that tangential component you change your sign, and normal component you don't change your sign. And then Wij is a correction term. It is introduced there to take care of the boundary value on sigma. Because if you use these 2 guys to contrast solution in whole space, its boundary data its value on boundary will not be 0. So we need some boundary potential to take care of this. So here, this is boundary potential. S is the Gaussian tensor, phenomenon solution in Rn, and Kn is the Golovkin tensor, which is the Poisson kernel for boundary value. So this thing is given by this formula here. And so this is a heat kernel. This part is something integrated over sigma times 0 to xn interval. And then there's something which has a delta function in time. This corresponds to Helmholtz projection. So this term here is not a function, it's a distribution. So this is our first formula. If we estimate this formula directly, we get some singularity near boundary. And this is very bad singularity, it's not integrable. And so we want things to be integrable near boundary. So it's not desirable. And so what we did, the trick was to remove the time integration using this formula. I don't know if there's a name for this formula here. So here gamma is the heat kernel, and P is the Poisson kernel for heat equation. And so this integral will give us gamma again, but based at the reflection point. But there's a similar formula for Laplace equation. So this is very useful for us. But I don't know a reference for this. I know a reference for the elliptic case. Okay, anyway, it's simple. And then using this formula, we can give a new formula for our correction term, Wij. So now there are 4 terms here, heat kernel. This is a Lewis transform of heat kernel. Gamma Ij is IRJ gamma, which we introduced when we talked about the ocean tensor. But then Ci was introduced earlier. Is this integral over sigma times 0xn? And then Hij is new. Is this integral in whole space? But we have Ci here, and we have fundamental solution here. So this guy is basically Lewis transform of Ci. So this is our second formula. We were very happy with this same formula until we found the following. Ci and Hij, they only have 1 mass n tangential decay. So it's not in L1 in Y prime. So this is very bad. So we have only this decay. We cannot contrast solutions for Navier-Stokes. So we want to maximize the tangential decay. And what we do is that we have to combine the last 2 terms together. And then last 2 terms together is combined called Hij hat. And then we had to do a few changes. And then it turns out to have these 2 formulas depending on whether or not J is less than M. And then di beta M is defined to be this integral. This integral is very similar to the integral for Ci. And the only difference is that this derivative here is in beta. And here, beta here is J, here is beta. So this beta is always less than N. So let's go back to previous page for Ci. So this is Ci formula here. This is normal derivative. This guy here is tangential derivative. We don't like normal derivative. We like tangential derivative because for tangential derivative, we can integrate apart. This guy can be moved to this guy here. For normal derivative, we cannot do that because this is not whole space. So tangential derivative is always better. So this guy here has better estimate. So we now estimate this Dijm. So we had to do some space partition and then integrate apart to estimate. We first estimate tangential derivatives and then Yn derivatives. And then to estimate Xn derivatives, we need to use some formulas. For example, we want to compute the divergence for these guys. So this will give us our first estimate. And second estimate is that we first also estimate the pressure tensor. And then we use these things. The symmetry for Gij is then proved using the first estimate and the pressure tensor estimate. And finally, we use the symmetry to refine the estimate, the first estimate, and also use the divergent Fourier condition. Well, that's the end of my talk. Thank you.
Okay, so let's thank Tai-Peng for his nice talk. Are there any questions for the speaker? So it seems to me that such Green's tensor is not unique, right? So you can have different type of.
Yes, we can prove it is unique because
it's unique.
Yes. Let me see. In what sense it is unique? You had to work for every intro data. So I think we just need to. So to prove uniqueness, we need this theorem. And basically, I think this part is enough. So this solution formula should work for every such intro data. And you also allow U0 to be not divergence free. Then this thing will be unique. Because basically you can use any test function here.
So if for U0 is divergence free, then this becomes the Green's function constructed by so unequal?
No. What we claim is that after integration they are equal. We are not saying that
after
restricted
integration,
divergence free guys they are equal. No. So
okay.
it's only after integration. So it's the same here. This guy here is not zero, but after the integration, the contribution of this part finishes.
I see. Any other questions? So I have another question. Are there any results about other boundary conditions like Stokes boundary conditions or Lyon's boundary conditions?
It's we have not thought about that yet. I think it's too early. So this is the first result. Maybe I don't know, next year.
Okay. Great. Other questions? All right, so let's thank Tai-Peng again for his nice talk.
Thank you.
Thank you.
Thanks.